Now, you have already looked at this example, and this example is just a refresh. All the member that you divide, they are all lying in the same axis. And we've gone through the process of how to get the structure stiffness matrix with these two elements and how to consider the boundary conditions. If this is fixed spin, how do we consider? And finally, how do you get the critical load by setting the criteria determinant of the structure stiffness matrix equal to 0. And also I briefly go through with you this example. Now this example is basically what I want to show with this is you have members like this and member like this and member in this way. These both are vertical, this is horizontal, and you have column which is subjected to axial force, and you have beam where there is no axial force. So the stiffness matrix that we have to use for this and this will include the part due to P, but for this we will not include the part due to P because this one there is no axial force. Okay. Then we also look at, I also mentioned about the structure displacement at structure level, and then when we break them into one element, we can have more than one here, two, okay? But we use only one, and to show the process. And here you have the structure stiffness, structure level displacement, and also the nodal forces. So here we use W to represent the structure level forces, the loading, and capital delta to represent the structure displacement. So structure displacement has 3. Now displacement also include rotation. Okay. So rotation at this joint and rotation at this joint is delta 1, delta 2, and then the translation of this joint and translation of this joint is delta 3. We only indicate here because here and here they have the same delta, same displacement. This point and this point, the same displacement when this frame sway. Okay. Then the corresponding nodal forces. Then when we break to element level, this is where you need to be careful with the positive directions. This is x-axis of this element, and this is x-axis of this element, and this is x-axis of this element. So x-axis must start from a beginning point, points toward the other point. Okay. So x-axis start from here for this element, x-axis start from here for this element, and x-axis start from here for this element. So that defines the x-axis, x, x, and x. Then we need to find the y. Okay, x and y, x and y, then x and y. So x and y must be defined. Then only the positive directions for nodal displacement at element level we can define them because it is opposite to the y-axis. So that's why it is pointed here, pointed in this direction. This one is pointed in this direction. This one is pointed in this direction. And also here, this one is pointed in this direction, and this is pointed in this direction for the displacement. They are pointing in the opposite to the y directions. For this member, x is here, y is here. So the opposite. For this, x is here, y is here, this opposite. For this member, x is here, and then the y should be. Now we have to look at If you use this is your x. This is your x. This is the x. And this will be the y. This will be the y. Okay. You follow your right hand rules. Your right hand rules. In this one, you point to the x directions. Okay, you point to the x directions. Okay, this is x, y, and z. So this one is your x, this is your y. And that's why this one like this. And here, this is the x. And this finger, this is a z, x, y, and z is pointing towards the screen here. So you have x, bend a bit, x, and this is the y for this member. That's why the positive delta for displacement is like this. And for those who are online, you cannot see me. Okay. And I will. Then this is for this one. Why it is like that is because your x is like this, your x is like this, and your y is, don't have to turn like that. X, this is the x. Look at this. This follow the x, and this will be the y. Okay. This middle finger should point towards here. Then this is how we define the positive directions. Okay. Then the rotation, they are all clockwise. Rotation are all clockwise as positive. So this is important later when we want to relate this element displacement to global structure displacement. The direction, are they the same or are they different? When they are different, then there must be a negative. So if they are the same, then they are positive. So this is important when you want to relate to the structure displacement. Now, in order to relate to structure displacement, we need to form a matrix that we call the B matrix. Okay, the B matrix. I'm going to show to you now the B matrix. Okay. Now, in order to get the K of element, okay, in structure level or in a global level, this is when we transform it into the global level, which is at the structure level. This is still element. Then we have to have this B transpose K at local level. Then the other one will be B. Okay. So this is to get from element 1, 2, and 3. They are at different orientations, but with this B matrix, which represent how you transform into global, you have to do this. Then after you get this, then you get the element level already transformed, then you get the structure level. You get the structure level big K, then after that determinant K 0, then you get the P critical. Okay. So that is the process. So now how to get B? B is actually relating the element displacement to the structure displacement. B is relating the element. This is at element level. Element displacement This is the structure level displacement. So we need to do this one by one. Element 1, the B will be different compared with element 2, and element 3, the B will also be different. In general, they will be different. Okay? So how to get the B is you look at the element by element, especially the displacement, and you compare with the structure level, then you can form the B. So B will be in the form of matrix. Okay? So the size of B matrix, the size of B matrix is 4 rows, and the number of column, it depends on how many structure displacement you have. So the size of this matrix is always 4 rows because element has always 4 displacement, but the structure displacement, which is non-zero, depends on the problem given to you, how many of these. So N here is the degrees of freedom. DOF, degrees of freedom of the problem. Which means how many non-zero displacement do you have? In the example that I show you just now, N is equal to 3. Because we have delta 1, delta 2, delta 3. So this size here, how many columns depends on the problem. But the rows is always 4. Because delta here, for each element, there are only 4. 2 at one node, 2 at the other nodes. Okay? This delta is always delta 1, delta 2, delta 3, delta 4. Okay? Or delta 5, delta 6, delta 7, delta 8, and delta 9, 10, 11, 12. So always 4. Always 4. Okay? This is related to our clockwise. Okay? Each of the element, they have 2 displacement here, 1 displacement, 1 rotation, 1 displacement, 1 rotation. Always there are 4 only. So that's why the row is number is 4, but the column, which is depending on this delta, the structure, how many non-zero structure displacement, and it is equal to the degrees of freedom of the problem. Okay. So then after you get this, then you can do these multiplications. From the left-hand side, the transpose, and from the right-hand side, the matrix itself, and multiply with the K. K is the one that we've seen in the lectures. It will be given, okay? If for beam, we only consider the flexural part. For column, we have to add the one that we consider the effect of axial force. So this is the main thing that you need to be aware of. So how to get this B? This is the one that I'm going to show you using that example. How to get B. Now the main idea here, how to get B is you go one by one. Element 1, start with element 1 first, element 2, element 3. Then you look at this element will correspond to the structure level, this one. Yeah. This element 1 corresponds to structure level, this one. Element 2 will correspond to this. Element 3 correspond to this. So if you look at element 1 and this, so now you can form the B by looking at delta 1 is equal to what? in the structure level? Delta 2 is equal to what in the structure level? Delta 3 is equal to what? Displacement at the structure level. And delta 4 for this element is equal to what at the structure level? Then you go to element 2. You go to element 2, which is corresponding to this. Then you look at for element 2, the delta 5 now. This is always 4, but we change the number. Delta 5 now, because this is finished with 4. So the next one, you add 1. Delta 5 is equal to what at the structure level? Delta 6, delta 7, delta 8. So you form that equations first. Then from there, you write in matrix form, you get the B. The last one, element 3. Element 3 will be corresponding to this element at the structure level. So now you look at delta 10 and delta 9 is equal to what at the structure level? Delta 10, delta 11, delta 12. Example, after that I'm going to show you in the whiteboard. Delta 1 is equal to 0. It is fixture. Delta 2 equal to 0. Then if I jump here, delta 11 equal to 0, delta 12 equal to 0. And delta 3 here equal to, delta 3 is the translation. We correspond to this joint, it will equal to, remember here, this displacement and this displacement, they are the same. So this is also have translations of delta 3. So delta 3 here is equal to this delta 3, but the directions here, this is like this is like that. So delta 3 here is equal to negative delta 3 at the structure level. Delta 4 is the rotation is equal to delta 1. Let's settle with element 1. Now you go to element 2. If I ask you now, delta 5 is, what is delta 5 to here? For this element now, so delta 5 is the translations in these directions. And when you compare here, delta 5, when it comes here, there is no displacement of this element, of this joint in these directions. Okay, so delta 5 is 0. Delta 5, 0. Because we don't consider actual displacement. Okay? We only consider translation and rotation. So delta 5 is 0. Delta 6 is delta 6 is the rotation equal to delta 1. Yeah, delta 6 equal to delta 1. Then delta 7 again equal to 0. Delta 8 equal to delta 2. So that is the second set of equation. From there, you get the B matrix for element 2. Then the last one, element 3. So start with delta 9. So delta 9 is equal to delta 3. Delta 10 is equal to delta 2. Then 11 and 12, because this is support, so 0, 0. Okay. So that is the process, and it is very time consuming, one by one. If you have 3, then you have 4, 5, 6, then all this process to get the B must be repeated for each element. Okay. Here, because we already consider the boundary condition, the support conditions when we form the B matrix. So if you remember the first example, we form the whole matrix first, then we consider the boundary conditions. Here, we already consider the support conditions at element level by putting delta 1, 0, delta 2, 0. Already considered. Delta 11, 0, delta 2, delta 12, 0 means we already consider the support condition at the element level. So when you get the structure stiffness matrix, the big K is already consider the support condition. No need to delete column and row again. Okay. We can do the same thing like the previous example. Don't consider this first. Form the big K, then only delete. You will get the same thing. But here, what we do here is the B matrix already consider the support condition. So the final K that you get already have the information about how the structure is supported. So you can take determinant of that K, in this case, directly equal to 0. Okay. So that is the process of getting B. Okay. So now I'm going to show you how to get the B matrix form from the equations that we have. So you have 4 set of conditions: delta 1, 0, delta 2, 0, delta 3, negative, delta 3, delta 4, positive, delta 1. So that is the equation: 4 set, 4 set, 4 set. Then you can write them down in matrix equations, then is where you get the B. Okay, so that is the things that I'm going to show you next. But I need to look at this, so I'll give 1 second then. So let me write on the whiteboard first. I think for those who are online, you cannot see because after that I will change the camera. Okay, now I want to write because I want to refer to this. Okay, so if I write down for element 1, okay, I use this symbol, and in here we use the symbol. So delta 1, 0, delta 2, 0, delta 3, negative, delta 3, delta 4 is delta 1. So this is for element 1. Let me write down for element 2. Element 2, delta 5 is what? Delta 5 is 0. Delta 6 is delta 1. Delta 7, 0. Delta 8 is delta 2. Okay. So I hope you confirm this. Okay. And for element 3, delta 9 is equal to, delta 9 is negative, positive delta. Delta 9 is delta 3. And delta 10 is delta 2. And delta 11, this is support, delta 12, 0. Okay, so now let me show you how to get the B matrix. Okay. So now you see on the whiteboard, I show the relationship that we will use to form the B matrix. This is actually, we can write this in matrix equation form. And how do we write this? We write in matrix equation form is delta for element 1 will be delta 1, delta 2, delta 3, delta 4. And you put in matrix form, this is always, the number of rows is 4. And this delta, the size of delta here, this is a vector. This is a vector of delta 1, delta 2, delta 3. Okay. This is the size, so the n is 3 here. N is 3 here because the structure non-zero displacement, there are 3, delta 1, 2, and 3. Okay. So now you look at this, delta 1, 0. So it becomes 0, 0, 0. Okay. Second one, delta 2, 0. So it's also 0 multiplied delta 1, 0 multiplied 0 multiplied delta 3, 0. This is just expand these equations. You expand these equations into zero delta 1 plus 0 delta 2 plus 0 delta 3. So if I expand that, then I put 0, 0, 0 into that matrix. Then this one is there's only delta 3 involved, no delta 1, no delta 2. So you have delta 1 is 0, delta 2 is 0, only 1 with delta 3. And the final one, delta 4 is delta 1. So the other 2 and 3 is not here. So it becomes 1 for delta 1, 0 for delta 2, 0 for delta 3. Now let's write for element number 2, the B matrix. So class, you have this B matrix now. This is the B matrix for element 1. Always 4 number of rows. The column is 3 here because the degrees of freedom is 3. So delta 2, you start with 5, 6, 7, 8. The number of row is always 4, 1, 2, 3, 4. The number of column is 3 because you have delta 1, delta 2, delta 3. So how to get the B matrix? Look at element 2. So 5 is 0, nothing to do with. So delta 5 is 0, 0, 0. 5 is 0. Delta 6 is delta 1, so it becomes 1, 0, 0. Then delta 7 is 0, then it always 0, 0, 0 again. Then delta 8 is delta 2, so become 0, delta 1, 1, delta 2, 0, delta 3. Then the third one, finally, the third one, we have the third one. So delta 9, delta 10, delta 11, delta 12. So delta 9, delta 10, delta 11, delta 12 equal to 4 rows, 3 columns, delta 1, delta 2, delta 3. So what is the content of that matrix? Delta 9 is delta 3, nothing to do with 1 and 2. So 0, 0, 1. This one is 0, 1, 0. This is 0, 0, 0, 0, 0. Okay. 0, 0, 0, 0, 0, 0. Okay. So this is how you get the B matrix. Okay. It's a very lengthy process. Okay. But also, of course, in computer program, when you key in computer program, like the final element that you are using now, when you key in the data already, this information already stored in the memory, then they know how to form this in programming. We use programming. Now we are using hand calculation, so it's a very lengthy process. Okay. So now you have this is your B matrix now for element 1. And this is your B matrix now for element 2. And this is the B matrix for element 3. So remember, what is the purpose of this B? This is just, you get it for some reason for that. For the purpose for us is because we want to get this K element at global level, transform it, and this is when we use this B transpose, K at element level, K for element, but this is local. L means at element level, then multiply with B. So this is when we need the B4. So once you have this, you have to transpose this. So transpose is row change with column. Column change with row or row change with column. Okay. So example of this transpose will be, so B1 transpose. The size of this matrix now will be 3 rows, 4 column. Transpose now. So when you transpose it, so it becomes 3 rows, 4 column. So the row become column 0, 0, 0. Second row becomes second column 0, 0, 0. Third 0, 0, 0, negative 1, 1, 0, 0. Then the same thing for the second one and the third one. Then one by one, this one multiplied to this for element 1, multiplied with the corresponding B for element 1, transpose on the left-hand side, then this on the right-hand side. Now, the sequence here is important. Here, followed by this, followed by this. Okay? You cannot do this, huh? You cannot do B transpose B first and then change to K. This is not the same. Matrix, the sequence you must follow. Okay. It's not like A multiplied B multiplied with C. You can change A, B, C, the sequence. Here, you must follow the sequence. This one multiplied from the left-hand side. This one multiplied from the right-hand side. It is very important to follow that sequence. And this is, again, I emphasize, you must eat properly because this is very time-consuming. You must have enough energy. You must sleep properly. You must have enough ink in your pen. Okay? Make sure. Then you multiply this, make sure your calculator have enough battery. Okay. But if you understand there are many 0, 0, 0 there, you understand if there are 0, 0, 0, many 0 there, then there is something good. When you have 0 means that particular multiplications you can omit, but you must know what is the effect of having 0 column or 0 row. Okay? But in principle, this is a very lengthy calculation. Now this matrix here, the size of this matrix is, what is the size of that matrix? How many rows, how many columns? 4. This is 4 rows, 4 columns. So the B transpose here now for this problem become 3 rows, 4 columns. So 4 and 4 you can multiply. And this one become 4, 4 and 3. So the final one, this one become 3, 3. This is 3, 3. Okay. You have 3, 3 because your degrees of freedom is 3 here. If your degrees of freedom is 2, then this final one becomes 2 by 2. If your degrees of freedom only 1, then this is only 1. Okay. So the structure stiffness matrix for each element is 3 by 3, the size. So you can add when you do the assembly. This is only to get the element stiffness matrix at structure level. You still need to assemble. Okay, you still need to assemble. So you need to get the big K by assembling. Okay, this assembling all this. And you already changed them into all the elements already 3 by 3 through this relationship. Then you can just add them together. Element 1, 3 by 3 matrix, add element 2. So this one is adding. Okay? For element 1, you add up. For element 2, then you add up again for element 3. So you add them up directly. Okay? So when you add the matrix, okay, you add the matrix that you form through this process one by one, then you get 3 matrix for the element 1, 2, and 3 already transformed into global coordinate system and just add them up together. Okay. So this is a process. Okay. So, and finally, to solve, then determinant of this K equal 0. And to find determinant 3 by 3, again, it is very lengthy process. You need to use cofactor, minor, and very lengthy process. Okay, so very lengthy process. So, but you need to know at least the procedure is to do this. Okay, so but you need to know at least the determinant for 2 by 2. Okay, 2 by 2 matrix. Okay, the determinant you have to know the 2 by 2 matrix, the determinant. How to get the determinant of 2 by 2 matrix. So if the matrix is A, B, C, D, so the determinant will be A multiplied with D multiplied with B minus C. So this one you have to know. Okay. 3 by 3, 3 by 3 is yeah. Now this is a process. Okay. Now there's one important part is this K matrix here, which is you use the K element here. For K element, if it is a beam, then you don't include the matrix which is due to axial force because there is no axial force. So, but if it is a column, then you have to consider. So when you add these things, you have to add properly. Okay, the bending part, add with the bending part, the matrix due to axial force, add with the matrix due to axial force. Okay, so that is the things that you have to take note of. Okay. So what do we mean by adding properly is you have to take note of this one. Okay. There are two forms of the K element. So one is like this, which you have to be careful which one is given to you. Okay. This matrix will be given to you. So this is for beam part. Beam doesn't have this, P0. So in our example, the horizontal member, we don't consider this. The vertical member, we consider. Okay. Plus this P. So when you add the structure stiffness for element 1, 2, and 3, so because you separate them into 2, so you add this one for element 1, 2, and 3, and you add this one for element 1, 2, and 3. Okay. And here, you must be careful here. There are L here. This L is for the length of the element. Here also there is L. If the length, they're all the same, then it's okay. If the L length are not the same, then you have to use the actual length of the element. This is one form of the equations. The other form of the equations, depending, because it can be given also in this way. This is another way of writing the element stiffness equation, but we have changed this everything to force and everything that to displacement. Then inside here, L comes out here. L comes out here. This one, L out here. Inside there is no L, only numbers. But this L and this L is for that element. So if element 1, the length L is different than element length L, then you have to be careful. Okay? Use the length for that particular element. So either this one or this one can be used. This one, L is inside the matrix. The next one is L is outside the matrix. So for this problem, for example, the L that we see there, this is the whole L. Yeah? This is the structure L. The L that we see in the stiffness matrix is the element L. So this is the whole structure L divided into two elements. So the L in that equation is L over 2 for element 2, L over 2 also for element 1. Use that length. The next one here, for example, here, this example simplified length the same, length the same, length the same, all L, L, L. So when you substitute in the element stiffness equation, so this, for this element, the length in the stiffness that you have to use in the stiffness equation is this length, L. For the beam, if this length, L, and for this element number 3 is this length, L. So if this length is 0.5 L, then for the beam, have to use 0.5 L. Okay, this is what I mean, the L here, this L. This L is for each element might be not the same. It might be the same, might not be the same. Okay, so be careful, especially if you are using symbol. If you are using number, give you 6 meter, 8 meter, then you use that 6 meter, 8 meter. But you are using L, 0.5 L, 0.8 L, so have to be careful with this L. This L is not the structure, but this is the element L. So that is the thing that I have to take note. Other than that, this matrix method is not that complicated, but very tedious. It is suitable for computer. Okay? Use with computer. Now the detailed example, detailed process of this is given here. Okay, so I show you that part so that you can refer to that particular. This is in chapter number 4. It is on this particular section 4.5 of this books by Charges. The detailed process I will show here. What I explained just now, I all explained here. In section 4.5 for this example, what I've gone through with you, they are all explained here. Okay. Right until this is class again, sorry, this is a bit not clear. So right until the final structure K. Okay, but here, of course, if you are using symbol again, we don't use number, so it becomes the expression sometimes become very complicated. So there are some introduce some of the simplified terms here to make it simplify. I think the K matrix, it is 3 row, 3 row, 3 column, okay, as what we have seen, because the degrees of freedom is 3. Then to solve this, there are some terms introduced here. Okay, so to solve this, then finally they get the answer. It is a cubic equation, yeah, because if you have a determinant, if your degrees of freedom is 2, it is quadratic equation, which means you have 2 solutions for P. Here this is 3 by 3, meaning that you have cubic. This is 3 by 3 means you have 3 solutions for P. So we choose the lowest one. Now the lowest one as the solution, but you have 3 solutions for P. The higher one has no meaning, but the lowest one is the one that will be used as buckling. The higher one has meaning as mathematically, but the one that we want to determine buckling load from here, if you get the determinant, it will be a cubic equation. Yeah? You have P to the power of 3 appear there. So when you solve, you have 3 solutions, and we choose the smallest one. So this is where you can refer to what the detail that I explained here, how to get the B, how to combine them, and what is actually the K for element 1, 2, and 3. For beam, you don't have this part. Beam, don't have this part. For column, element 1, element 3, you have this part. And when you combine this to get this, combine this is nothing, combine this to get this. And finally, the big K is these two already right in this form. Okay. So please refer to that. Again, this is on section 4.5. Okay. 4.5. Stability of frame by matrix analysis. So I will pause here for a while. So if you see any questions, and we take a short break. If you have any questions.